Okay, good afternoon, everybody. I guess we can start. And without further ado, I will leave the word to Professor Manzoni for this second lecture. And I notice you all that from now the recording is starting. So, Luca, please go on and have fun, everyone. In case of troubles, just write in the chat or write a private message to me.
Thank you, Michael. Welcome, everybody, to this second lecture of this short introduction to the Julia language and some of its libraries. Today, we will have a short tour of some useful Julia libraries. In particular, we'll see how to interact with Python and AI code using PyCall and AICall, how to benchmark our code. We will start doing some plotting, just some basics. Then we will move to libraries more related to the data science and artificial intelligence domain, particularly how to work with data frames and how to build neural networks easily with Flux. So let's start. We will have to import, because we will use during all the lecture, the data frames, plot, and statistics packages. And also we will start working on how to call Python code from inside Julia. And to do this, the best possibility that we have is to use the PyCall package. And among the functionality of PyCall, we will see how to import and use Python built-in functions, like we'll see some map and some others, how to import entire Python packages, or how we can write Python code directly and have the result being available to Julia, and how type conversion between Python and Julia works. And since we may want to use some large arrays, for example, using NumPy, how we can implement the passage of information from Julia to Python without having to copy the information. So let's start by looking at how we can import some Python functions in Julia. If there are built-in functions, we can use the pbuilt-in function made available by the PyCall package, and as a string, the name of the function to import, and we can assign it to Julia variable. In this case, we have imported as PySum, as PyMap, the sum and map built-in Python functions. And as we can see, we can actually call PySum with a Julia array, and everything is converted from Julia to Python and back. So the sum here, PySum here, is actually calling Python code. But as you can see, this happens in a quite transparent way. We don't have to know that we are actually using Python here. Actually, the integration between Python and Julia is even more profound. For example, here we have the application of the map function that applies a function given as the first argument to the collection given as the second argument. We can see that here we are giving a function x mapped to x squared that is a Julia function, an anonymous Julia function, and a collection, in this case the range between 1 and 10, which is also a Julia type, as arguments to a Python function map. And as a result, we have an Python object. This is correct since Python map in Python 3 is lazy in the sense that it turns something that can be iterated over without applying it directly. And we can see that we can iterate over this map object and obtain exactly the result that we want. So as you can see, this conversion happens automatically most of the time. Type conversion between Julia and Python without any problems. And in fact, we can also import entire Python libraries, for example, entire Python modules, using the function pyimport. You can use pyimport, for example, the math module on, and this is now assigned to this variable, which is Python module, and we can call the functions contained and assess the variables, the constant in this case, contained into the Python module without any particular problems. So we can call the cosine function of Python. We're using the pi constant defined into the math packages in Python, and everything works. So for now, we have seen how we can import Python code and use it quite easily. But in fact, we can also do more, because we can actually write Python code inline inside Julia by using this particular string starting with pi. So as we had seen last week, we had a regular expression prefixed with an R. Here we have a string macro that uses the pi prefix before a string to execute the code contained as Python code. So for example, inside here we have Python code, where actually this comprehension, we have I plus 5 for all the numbers between 0 and 9. And as you can observe, this code is evaluated in Python, and the result is converted back as a Julia data type, in this case a 10-element array. This automatic conversion can potentially, in some cases, may not be what we want. We will see one case when we don't want this automatic type conversion. And if we want to avoid this automatic type conversion, we simply add after the string of Python code an O, and you see the return is now a Python object. But this is not limited to simple Python code. Well, not so simple, because here we have this comprehension, but not only to simple Python codes, but also to entire functions. So we can define a function in Python that takes as argument another function, so a higher level function, and has a keyword argument. We have defined it in Python. When we want to call it, well, we have to actually move it back from Python to Julia. So we use pi, the name of the function, and then the result of this expression will be a Julia function that can be called, as we can see, with a Julia anonymous function, we can use keyword arguments and everything works. And in fact, if we assign to a variable this pi and Julia function, from now on, we can use it directly and everything will be transparent. We may, without looking at the implementation, we may not even know that we're actually calling a function that has been defined in Python. So I see that there is a question in the chat. Is there a reason to import Python like this, besides familiarity with Python and importing an existing Python code base? Are there things which are generally easier in Python than in Julia? Well, might think that the main reason for this interoperability is that Python has a lot of library and there is a lot of code already that is already written in Python. So we may want to use that code without rewriting everything and maybe moving an existing code base from Python to Julia a piece at a time, and this allows us to do this without too many problems, since the interface remains the same. Another possibility that we will see is that, for example, for there are some very good Python packages, and okay, there are some very good Python packages like matplotlib and Tensor Flow that we may want to use directly. So what's the behavior for non-standard types data structures? In general, you can also import this. It is, I would say, not necessarily always immediate, but not too difficult. It is, another question, it is also possible to do the same with R. It's the next part of the lecture, how to do this with rcall. And does the interoperability works well? Well, I think it works quite well, given that, at least in my experience with other languages, this interoperability is quite easy to perform. Can we also use PyCall for more exotic libraries like SymPy? There is exactly a package for that is a complete wrapper from SymPy, so you don't even need to use directly PyCall. But yes, you can use it. So one reason we may want to use Python, in addition to all of this, is that we may want to use, well, NumPy, actually, because NumPy is actually mainly implemented in C with the Python interface, so everything is quite fast, well optimized, and so on. So we may want to use some NumPy functionalities, and also many libraries used for data science and machine learning uses NumPy. So what we may want is to avoid, every time we move between Python and Julia, to copy an array. And this copy is actually, if we use standard Julia arrays, is actually necessary because of the fact that in Julia the array are stored in the column major order, while in NumPy they're stored in the row major order. It is the layout in memory is different. And while you can pass to Python arrays in column major order, many NumPy functions want the data in a row major order. So what we have is that there exists, with a little bit of code to write from the Julia side a way to avoid the copy. For example, here we import NumPy and we create XS as an array, as a two-dimensional arrays of zeros. And if we use the O at the end of here to avoid the automatic conversion, we can wrap everything in a pi array. This pi array actually has the same abstract array interface as all the arrays in Julia, that is, all the function that works with any kind of array in Julia also works with this pi array, except that when moving from Python to Julia, there is no copy, where they are actually using the same memory, which may not be significant in the case of a 10 by 10 array. It can be significant when the amount of data is a lot bigger. And one thing that we will not see now, but if you are interested, I encourage you to read the PyCode documentation, because it is, in my opinion, well written, is that it is also possible to write code in Julia and then use Python to call Julia code. So the reverse, instead of embedding Python inside Julia, embedding Julia inside a Python application. And if you are familiar with packages like matplotlib, you can use the package pyplots that provide a complete wrapper of matplotlib using behind-the-scenes pycall, so you don't have to do it by hand, but you have a Julia package that actually calls into Python, but that works and feels like Julia. Is there any question regarding this part on Python?
Excuse me.
Yeah.
I actually not understand. By using a pi array, we avoid the copying, and this is important just because when we have a large array, we skip the copying. We have less data exchange, right?
Yeah. Yes, because usually the arrays in Julia and Python are stored in a different ways in memory. When you move an array from Python to Julia, what you have is that you are actually copying the entire array, which maybe, first of all, if we perform it a lot of time, can be slower because we're always copying. We can have a problem that the array can be extremely large, and so we don't want to keep actually two copies of the same data. So what we may want is simply to use this parray type to work without performing a copy in the same array that is a NumPy array and an array that is usable by Julia.
I see that we pass as argument of pi array a pi object, which is an array in Python, right? Because
we use this O at the end to avoid the automatic type conversion, which will result in a copy otherwise.
Okay, thank you.
Okay. There is another question. Can I call variables I define in one string? And can I call variables? So moving between having the same variables in different strings. Is that the meaning of the question? Okay, well, we're actually doing this because here we have a PyString in which we have XS, and here we are using it. These days, does this answer the question? Okay. So, okay, so as you can imagine, apart from Python, another very used language for working with data is R. And in some cases, we have that we want to use some R-only package. For example, it is quite famous, the ggplot library for plotting. And we can actually use R code in Julia using the package rcall, which works a little bit different than pycall, also because R works a little bit different. So we have mainly two ways of interacting. One thing is to use two macros that are called rget and rput to import a variable from R to Julia and to put a variable from Julia inside R. We can use rimport and rlibrary to import libraries in Julia, R libraries in Julia. And similarly to pycall, we can use R, capital R, before a string to interpret the string as R code. So for example, let's say that we have defined an array X and we want to make the array visible to R. We use X and array put and the name of the variable. We can use multiple variables here. And the variables, the array X will now be visible. We have created a corresponding copy in the R environment of X. And in fact, we can now use it in this I code in which we assign to Y the maximum of the entire array. And if we want to access Y, we simply use rget. Yeah, I see a question.
Yeah.
So I put and rget I used to move variables between Julia and RNA space. Exactly. Yes. You have to, if you want to make a Julia variable available in the R namespace, you use rput. If you want to get a I variable and put it into the Julia namespace, you use rget. Rget also allows type conversion. Well, in Python works same. There is almost always a copy, except in some cases, like when you use the same memory. It's better to okay. So as you can see with rget, we actually have correct type conversion and we get the result. One interesting thing is that we have seen in the previous lecture that we can use string interpolation with the $sign and then a piece of Julia code inside the parentheses. Well, we can use string interpolation also when defining R code. So here, before calling R, we are evaluating this Julia code, which actually sums 9 to every element of the array. The array is then converted to R and then assigned to Z. And then we get Z. So we can, if you think about it, this means that we can actually build a piece of R code at runtime using string interpolation. But as with Python, we can also move functions between R and Julia. So suppose that we have a function that works for that we want to exploit to R, a Julia function we want to exploit to R. Well, we simply put the function, and then the function is then available inside R, and it works. And if we want to do the reverse, we have a function defined. Okay. I see a question. The Julia instance for a variable get converted to R integer. I'm asking because R allows to introduce 32-bit integers. I would have to check this one because I don't remember. Sorry, but I don't remember how this type conversion. So if we want to move a function from R to Julia, well, suppose that we define this function, which simply sums two elements. For in R, we get the function, and we can use it in Julia. And an interesting thing is that Julia is quite famous because of its support for data frames. In fact, I think that data frames are more or less the state of the art when we talk about structures to manipulate data. And that's why, for example, in Python, we have pandas that provide something similar. And how does this work in Julia? Well, Julia has a data frame library. And suppose that we want to create this data frame df. Well, let's get it. And as you can see, we have something which is a data frame. So we can move between R and Julia data frames quite easily, actually automatically. And this links then to the next topic of the lecture, that is how to manage data using data frames in Julia. But before continuing, is there any question about this part? Okay. So, moving forward, let's talk about how to manage data in Julia with data frames. Well, we can simply create, that works very similarly to data frames in R or in pandas. And we can simply create an empty data frame, but obviously this is not as interesting as a data frame containing some data. So let us generate some data. For example, we get position from 1 to 10, a random number, random y coordinate selected in a uniform way between 0 and 1, and a second random value obtained from a normal distribution with mean 0 and variance 1. So what we obtain is this data frame that with 10 rows and 3 columns, and by default we have x1, x2, and x3 as columns. but maybe we want some other names for the columns, and here we can use the function rename, and we can see that we have okay, I think in the chat we have an answer to the question. The convention is int64 coming. To the previous question on the data types for R. While continuing here, we have that we can use the function rename with a bang at the end, meaning that we are actually not creating a copy, but we are modifying, remember this convention, to adding a bang at the end of the name for a function that modify the arguments. And we can modify the name of the columns of the data frame by passing an array of names. This array can be an array of strings, or, as in this case, there is an array of symbols. This is the symbol X, the symbol Y1. If you want to use the subscript 1, you can, if you want to use the subscript 1, you can use like in LaTeX, and you prefix everything by backslash. So here we have new names for the columns. Here we perform the renaming, and as we can see, we now have renamed all the columns. But we could have done the same at the creation time by adding an additional argument, an array of strings or symbols representing the column names. So here we create the same data frame actually, with the same data, without using the rename, but directly naming the columns. And how can we access the columns of a data frame? Well, we can use the dot notation, so dot x or dot y1, for example, to get as an Julia array all the elements of the column. Is you can use also a notation that is more similar to what is array or dictionary access, which is actually saying take all rows and the columns is the one named X. But since there is this duality between strings and symbols in Julia, actually we can also use a string as an index. We have this automatic conversion between strings and symbol in mainly everything in the works that works with data frames. So before I continue, is there any question for this part on data frames, which is, yes?
Can you show again how the data was generated? I guess it was just a simple array generation. And then what did you do?
Yes. Okay, I used here collect 1 to 10 means actually 1 to 10 is not an array, instead is an interval 1 to 10. Collect takes all the elements. Is actually like in Python when you do list of something that can be iterated over, you generate the list of all the elements. A random 10 random number with uniform distribution and 10 random number with the Gaussian distribution. Then we want to concatenate everything with a horizontal concatenation. So we put everything, every one of those arrays will be a column. So I see a question: is data frames more powerful, efficient, or versatile than using one or multiple native Julia data structures? I think it is more versatile as with the using directly array, because as we can see, we have a lot of functions that are already available. We can have indexing with symbols, which means that can be more easier to write code for, and we can also have a lot. We can see a lot of easy way of working with data frames. So my opinion will be, if you have to work with data simply as array and you don't need any of the functionality of data frame, you can simply use arrays. But if you have some useful functionality that is made available by data frames, well, why not use it? So moving forward, one interesting thing is that we can, for example, add new columns to a data frame by simply assigning a vector of a suitable length. In this case, we need something of 10 elements. So for example, this x2 will be a random number between 0 and 1, uniformly distributed between, and 10 random number uniformly distributed between 0 and 1, all multiplied by 10. So will be numbers between 0 and 10. And we assign it to a column that is currently not existing, but now we have this new column added to the data frame. We may want to keep a little bit of order in this data frame. For example, now we have x and x2. So maybe we want to have x1 and x2, and we want to reorder the columns so that we have all the x before the y's. And to do this, we can use rename and select. In this case, rename, as you can see, this is a rename that works without making a copy, or works directly on the data frame, on its argument. So it's modifying its argument. We have renamed the data frame where the column x is now the column x1. And then we want to select columns in which order. As you can see, this will modify our data frame. First of all column matches this regular expression. We can provide a list of columns, or we can provide, in this case, condition, like a regular expression that must be respected for all the column names. So all the columns with x in the name, followed by the rest, which is noted by the columns. So as you can see, we have renamed the column x to x1, and we have reordered the columns so that we have x1, x2, followed by y1 and y2. So as you can see, we can easily rename and reorder columns inside the data frame. And once we have a data frame, we can also use function to describe getting some statistics about the content by column. So for example, if we use the function describe with argument data frame without any additional argument, by default, for each column, the mean, minimum, median, maximum, the number of unique elements or missing elements, and the data types are all reported. So now we have easily some descriptive information about the content of our data frame. However, we may not want exactly all those information, or maybe we want different information. And this can be also obtained quite easily via also via the describe function with now additional arguments. In this case, the arguments are the new column name, and the function to apply to a column to obtain the result. For example, we want for the data frame df, for each column, we want a column that is the mean, column that is the median, column that is the sum, and the column that is the product of all the elements contained. As we have name of the column in the resulting data frame, and function to apply to the data frame passed as argument. So here we have a symbol, x1, x2, that is the column names, the mean of the elements of all the columns, the median, the sum of all the elements, and the product of all the elements in the column. As you can see, this is quite flexible for providing in an easy way some statistics, or to apply some function to entire columns of a data frame. And in the case we want to go back to something that is not a data frame, but we want to work with, for example, after manipulating the data, we want to have a matrix, an array, we simply have to call matrix with the data frame as an argument, and here we have back our two-dimensional array in Julia. And before moving on, we will perform here our first plot. We have a scatter plot. Here we have scatter, and we can get the column for the x, the column for the y, and the same if we use the bang at the end. We say don't create a new plot. That will be labeled. Sorry. We say with the bang at the end, don't create a new plot, add to the existing plot. And as you can see, we have created quite simply a plot of the values contained into the data frame. And this is using plot.jl, which is maybe one of the more, I would say, the flagship way of plotting in Julia. But as I said before, we have pyplot if you want to use matplotlib. You can use ggplot by calling R, or there are also other interesting libraries. In particular, one that I like, even if it is still in the say not as complete as other libraries, is getfly.jl, which is inspired by ggplot, and for now the kind of plots that are available in getfly are not all the plots that are available, for example, in plots or pyplots, but still the plots are very high quality. And an additional note, now we're using the default backend for plot.jl, but actually, for example, you can use different backends. So you can, for example, exploit generate plot in plot.jl that are made with Plotly JavaScript library. Okay, so is there any question about this part? Okay. So continuing with data frames, we will now manipulate a little more the data frames, and we will see how to transform the data contained and to obtain some additional statistics. For example, we may want to have a simulation, let's see, or some kind of process that give us some result, and we want to push it into a data frame that collects all the results. For example, we have different experiments. We want to push the result into an existing. So let's take, for example, we want to generate 100,000 elements. Each element is a random number, is obtained in the following way. We generate random numbers until the sum of all the elements generated until now is smaller than 1. So we create a list in LM, which is an array of 64-bit floats. We create an array of random numbers whose sum is strictly greater than 1. And all the numbers are sampled from a uniform distribution between 0 and 1. And suppose that this is our experiment. And what we want is to push into the data frame the following information: the ID of the experiment. This is the first, second, up to 100,000. How many elements we had to add to each to go over 1 with the sum, and then the elements. And if we do this, as you can see, it is quite fast. We have this data frame with 100,000 rows and 3 columns with ID, length of the list, which is here. As you can see, we can use push with the data frame and the tuple, named tuple, that gives the value for all the columns in the data frame. So this makes quite easy to use data frame to collect information while we are, for example, running experiments. And suppose that we have collected all those data, and now we want to see exactly what is the sum of all the elements in the list, in each of the lists. We stored the entire list. We store the number of elements. We want to know also what is the sum. And here we have the ability to use the transform with bang as before, because we are modifying the data frame. X as the first argument, the data frame, and then we have this that we have seen before. We have the name of the new column and the function to apply. Notice now that we are using the function inside sum, which means don't apply it to the entire column, apply it row by row. To elements. So instead of performing the sum of all elements, of all the content of the column elements, create a new row, a new column where for each row we have the sum. So here we have the sum of all the elements in this list, this array, element in this, and so.
What if we want to drop the column elements after the transformation. Can we do it in one pass?
One pass, well, transform, probably yes, but what I do usually is use a selector in this case. As you can see, here we are using selector to remove one column. For sure, potentially, we could have removed, perform a transformation and then a select excluding the column that we don't need anymore.
Okay, thanks.
I would have to check if you can do it exactly with only one call to transform or not. But with transform plus select, you can. So, but as you can see now, we have, by default, this is called elements sum because we applied the sum function to elements. Maybe we want another name, and we could use a name, which would be better because we don't have to compute everything. But now, just to illustrate, what we can do is that we can use select to remove the column that we just created. And then we can use this notation, which is take the column elements, apply sum by row, and save everything in a column named sum. So we can control the name of the resulting column. And here we have sum. As you can see, the sum of all the elements saving the column sum. Okay. So we can obviously use then function that works on columns, since when we extract a single column, it is actually an array. And if you see, we see that actually as we increase the number of tiles, here we have only 100,000, we'll see that the average length of this list will converge toward constant E. We could have done also this in a different way. For example, we could have used the function the extract to compute the average of all the lengths. To use the function combine, what we have is we have combine column length with the function mean. What we obtain is a one-dimensional array. A one-dimensional is a data frame with one row and one column, while the only value is the mean. So why we may want to use combine instead of the simpler mean here? Well, because we can work with group by to generate for grouping data inside the data frame. In the meantime, I see that there are a few questions in the chat. Okay. Is a question about the use of the bang at the end of the method name. And what is the specific use of bang? Then avoid copying. Well, you may, that's a motivation, but actually it is only a convention to use the bang at the end of the function name to specify that it modifies the arguments. So we can easily distinguish functions that do not modify and functions that modify the arguments. And it is a convention inside all the Julia packages to always have the bang at the end of functions that modify the arguments. So not only for data frames. Okay. For going on how to group things, is there any other question?
Excuse me, you said that the bang is a convention for methods that do not change.
That change one of the arguments.
I thought it was the opposite.
No. If we have a bang at the end, the argument is changed. In fact, when we add, for example, a transform, we have added a column to the data frame. And when we use, for example, mean, we haven't modified anything. We have taken an array and we have computed the mean. We haven't modified the length. So the convention is things that modify one of the arguments I with a bang, but it is a convention. Is nothing enforcing it except that everyone when writing code expect this convention.
Okay, so combine, written as it is, creates a new data frame.
Yes, combines is used for, in this case, to create new data frame. We will see it here, because usually you want to take part of a data frame and combine the values inside the column with some function.
So like, for example, if we have huge data frames, in order to avoid the copying data frame time by time, we need to use functions that do not have the bang at the end.
No, if we don't want to copy, we need to use functions that have the bang at the end. If you don't want to copy, you want something that modifies its argument.
I mean, if the argument is modified without the bang, with the bang.
So you are not creating a new copy.
I do not create a new data frame by using the bang.
Yeah, but it is only a convention.
Okay, but it is you use it a lot. That's why I was curious. Thank you.
Yeah, because it's using most Julia libraries. This is well, actually every Julia library to work with has this convention. Okay. Which is quite important because you, in this case, you know where you are modifying something or not. Okay. So going forward, as with the data frames in R or Python, we can perform grouping. For example, we group by the data frame df with respect to length. That is, we create a new grouped data frame for each value of length, and we sort the values. So now let's create the grouped data frame. As you can see, we have first group of 50,000 rows for all the length that are 2, up to the last group with 14 rows of all the lengths that are 8. And we can pipe it. If you remember, we have this pipe symbol, pipe operator in Julia. To this function, this anonymous function, it is combine x, the argument, in this case the data frame, by length, where the length, we apply the in this case, length to the entire column, and we call it number of elements. And what we obtain is that we have computed for each length now for each length of the array, the number of rows that had that length. So we have 50,000 arrays with 2 elements, 32,000 with 3 elements, and so on. And then we can easily plot them by plotting an histogram of the length, where the y-axis is logarithmic, which is with most libraries, plotting libraries, we can specify, for example, that we don't want the legend, we want a certain title, and we want certain size of the bars. There are a lot of options for making the plot look exactly as you want. So, and with this, I completed this very short introduction on data frames. They have a lot more functionalities. For example, you can pivot a certain data frame, you can use very complex group by and so on, but I hope I give you the starting point for looking into data frames as a way of easily manipulating data inside your code. So, is there any question about all the data frame part of the lecture?
Sorry, just to be clear, the bang means that the method does not modify its arguments.
No, bang means that the method modifies its argument.
Okay, so I wrote it incorrectly. Thank you. Also, when you computed the mean before, that resulted as the Nepper's number.
Yeah. Yes.
It was the mean of what? I don't remember. Of the length?
Of the length of the sequences.
Okay, which was we just selected a row and calculated its mean, okay.
The column, not a...
yes, the column.
Okay.
And we would have got the same result if we selected the scribe, right? But it was tabulated in that case.
No, in that, well, let's see, because we describe, oh yeah, we describe we would add that information, but a lot of other information. So we would add also the mean of the median, the minimum, the maximum of everything. Yeah. So yes, we could have done this with the scribe. Yeah, we could have same, but as you can see, now we have a lot of additional information that we don't actually need for now.
No. Maybe when we have a large databases, we do not need to use the scribe. Maybe it's not advisable to use it. Okay.
It depends on what we want to do. If we need to get the information that are obtained by the scribe, when we use the scribe, or well, depends on what we want to do. Okay.
Okay. Thank you.
Okay. Is there any other question? Okay. If not, let's move forward with building a neural network from, actually, we start from scratch, and then we will use the facility made available by Flux, which is a machine learning framework written entirely in Julia. And You can also use TensorFlow JL as a wrapper for TensorFlow, but I think Flux it is better in the sense that it is more intuitive than TensorFlow. So one interesting thing with Flux is that it can compute the derivative of more or less anything you want to throw at it. You normally want to throw it. For example, we have this function, which is simply a polynomial. We can say we have this gradient function made available by Flux that we get the function and derive with respect to what? With respect to x. So we have the derivative of f. And if we plot it, what we actually obtain is the we will plot the third degree and polynomial, and then the second degree polynomial, that is the derivative. But how is this computed? Is this done by some kind of approximation? So, well, let's look at it. With this automatic differentiation, if we start with 3x cubed plus 2x squared plus 5, what we would have is that the derivative will be 9x squared plus 4x. And we expect a good differentiation engine, like the one in Flux, to actually compile down the derivative as 9x squared plus 4x. And if we look at the generated code, this kind with LLVM, we see that what we have is that we are multiplying something by 2, then something again by 2. We multiply this value with itself. We multiply everything by 3, and then everything by 3, and then we add the resulting two values. If we look at all the code generated, it's actually the same code that is generated if you write directly derivative of f equal 9x squared plus 4x, which means that we are actually getting the same code as in the case when we compute by hand the derivative and we write it as a function directly. So this means that we have an efficient way of computing now derivatives and so the gradient. And now we can move to actual building a simple neural network from scratch. Actually, what we will build now is simply a linear function with because we don't even have an activation function at the end, so we have a linear function with 2 inputs and 1 output. We have this weight matrix. It is 1 by 2 matrix of random numbers between 0 and 1. Then we subtract 0.5, so they are average 0. And here we have the bias term, which also random number between minus 0.5 and 0.5. And how is a simple layer of a neural network defined without taking into account the activation function? Well, is the weight matrix by the input plus the bias. And this is what we actually defined. And if we want to compute the difference, an error between what the expected output of our simple layer and the actual output generated by our simple layer, which we are represented by y and y hat, we can, for example, use this mean squared error. This is our loss function. All this part assumes some knowledge of neural networks. So we have these loss function, and we have this. We compute the expected output. We have input x and expected output y. We compute our actual output y hat as simple layer of x. And we compute the mean of y minus y hat squared. And what we may want to do is to actually compute the gradient with respect to W, the weights, and the bias. And we can use the function gradient as before, that is made available by Flux. And we say which function? Well, this zero argument function that is the loss of x and y. So we want to derive the loss. With respect to what? We say flux params, and we say what we want to with respect to what we want to compute the gradient. And as you can see, what we obtain is a structure that can be indexed by the name of, in this case, what we have the parameters, so W and B. This actually works with any number of parameters, so even with large networks. So what we obtain is that this is, if we had input to 3 and what we expected as output was to 4, this is our gradient, and we can have computed perform training as a simple gradient descent. What we have is, for the train function, we have our inputs, our outputs, and a linear rate eta, which is a keyword argument with default 0.1. And we simply compute the derivative. And we modify W and B by going in the opposite direction with respect to the gradient using this linear rate eta. Here we are using global. If you are familiar with Python, you know that if something defined in the global namespace, if you want to modify it, you have to use global. Here we are, since you are in a notebook, we are defining W and B all in the global namespace, so instead of maybe using a mutable structure. So here you are using global. I hope everything is clear. Okay. Okay. I see a few questions now. Is this derivative symbolic of numerical derivative? Can compute this symbolic? Actually, to keep tracks in keep tracks of all the operations that we had and to generate this certain output, and so you can compute something numerically. There is a very interesting paper, probably in the, I can, if I remember, or someone remembers me, in the revised version of this notebook, I can add a link to the paper explaining how it works. How complicated the function we may want to compute the derivative? Chair or partial derivative I comprehend? Yeah, more or less we can do. Also, we can compute the derivative with something that is while, that we compute with the while cycle and so on. I have used the gradient function to actually derive three based expressions that I use in genetic programming, and it works well. And I see that I've heard that global variables in Python sit in Julia. Is this the case? Actually, yes. The motivation, actually, if they are global, there are some additional problems with the fact that when you compile, you cannot perform some optimizations. So actually, if you wrap everything inside the method, performance can increase. So another reason not to use global variable, in addition to the fact that they are not, the global variable is something that you are, from a software engineering point of view, you may not want to use. I hope I answered most of the questions. Okay, thanks. So let's start to training our very simple linear function that if we feel quite bored, we can even call a simple neural network. Let us generate 100 random points, and let's visualize it in 3D. I'm not going into the detail on how the visualization works, but the idea is that here is our target, and here is, without training, what is our prediction. And then maybe we can perform training for 100 iterations. We compute the loss after and before. Before we have a loss of 73, after a loss of only 8. And you can observe, well, it is not perfect, but at least we are going near our data. You see, before we are completely nothing was of the predicted value was near our target value. Here, at least, we are getting near target values. Thing is, now, if you think about it, we have implemented a layer of a neural network. We can implement multiple layers completely from scratch now. We had defined here the weight matrix, the bias. We have defined what is the loss, and we say that to derive with respect to what. So do we need to do this every time we want to build a neural networks? Actually, no. And because we will see this example with MNIST, which is the dataset or well-known dataset of 60,000 images of handwritten digits that are saved as 28 by 28 pixel grayscale images. And Flux made easily to download this dataset, since it is quite a common dataset. This is not the first time I run it, so I see no output here. If it is the first time you are running it, you may see that you are downloading about 60 megabytes of data, or a little bit less. It's uncompressed is something like 60 megabytes. And if you are working in VM, now you have a slightly different notebook, simply because the VM does not allow to write into the Julia directory. We can take one of the images, and you can see this is the first image in the dataset, and this actually should be a 5. And suppose that we want now to build a standard convolutional, well, quite standard convolutional neural network, alternating convolutional and pooling layer, and with a fully connected layer and softmax for classification. So what we want to do now is to encode all the labels, which, as you can see, as a presented number, as one-hot vectors, that is vectors of length 10, in which everything is 0 except the index corresponding to the correct label. Now, since I'm doing this in real time, I'm only using 1,000 images instead of all the 60,000 images. I hope I will be forgiven for this simplification. And also, we want to change the shape of our inputs to be suitable for our convolutional networks. So we have height, width, so 28 by 28 by the number of colloid channels, which is 1 in this case because we have only grayscale, by the number of samples. And then split everything into mini batches. That is collection of multiple inputs, multiple images in this case that I processed all at the same time. So this is made simple by a lot of the functionality made available by Flux. So we can use the one hot batch, and we pass the set of labels, say all the labels that you want. So we have 1,000 labels and a set of possible values of the labels that are all numbered from 0 to 9. And now in Y we'll have a two-dimensional structure, and we have for each of the images a vector of length 10. Actually, in memory it is not represented as a vector of length 10, but as in a more compact way. And here, what we are doing is concatenate all the images. I am shaping them as a 28 by 28 by 1 by 1,000 array. So we have a 4-dimensional array now in X. And now that we have all the labels encoded as one hot vectors, and the inputs, all the images in the correct shape, we can split everything into batches, mini batches of size 32, for example, by simply use the data loader class. Say, okay, use this data as a tuple, the inputs and the expected output, and split everything into batches of size 32. And now we can move in building our neural network. And we will build it with a set of convolutional layers using 3 by 3 kernels, a padding of 1 in all directions. And we will use this notation where we have number of inputs, another number of outputs. Okay, well, okay, so what is the meaning of ... as suffix to images? The triple dot in this case is the unpack, because here we have an array of 1,000 images. We want to pass instead to horizontal concatenation 1,000 arguments, each one an image. So this is an unpack when we use it as for function arguments. So for example, if we have the array 1 to 3 and we unpack it, they will be interpreted as 1 in a function call as the 3 arguments 1, 2, and 3. Because we want to concatenate the images and not the array of images. Okay. So that's how we build our model. We want to chain multiple layers. And the first layer is a convolutional layer with a 3 by 3 kernel, convolutional kernel, which from one input channel give us 16 output channels. The activation function is the relu, and we use the padding of 1 in all directions. Followed by a max pooling layer, where we perform max pool in a shape of 2 by 2. Here I have another convolutional layer, the 3x3 kernel from 16 to 32 channels, still with the ReLU and padding, max pooling again, another convolutional layer, this time from 32 to 32, and another max pooling. Then we have a flatten, which simply, now what we have is something that is multidimensional, because we are working with a structure that has a width, height, and a number of channels. Now we want to flatten everything, because we pass the now 288 values to a dense layer, which has 10 outputs without applying any function, any activation function, so the identity function. And after that, we have the softmax layer, giving us the ability to select now, to give a probability distribution on the 10 different labels. And as you can see, this is quite easy to create these neural networks, because we simply have pre-built layers and we chain them. One interesting thing is that potentially we can write our own layer like before and add it to this chain, because, well, everything is implemented in Julia. And actually, if you look, for example, at the definition of the dense layer, it would be quite similar to what we have done before. We have this weight matrix, the biases, we had an activation function, and so on. So now our network, the model, has been defined. So before I continue, is there any question? Should I be equally efficient? Well, actually, since everything is implemented in Julia, if you are doing it by hand, using maybe for some of the Flux functionalities for the computing the gradients, for the training, what you obtain is actually more or less the same. Actually, the code for Flux is quite readable. And in my opinion, this is an advantage compared to when you use, for example, Tensor Flow. Because for Tensor Flow, you have that all the interesting part are implemented actually not in Python. But while here, you can look at the implementation and understand it without having to change language. Okay, I crash course on neural networks. I don't know exactly if a crash course, but I can find a few courses that it was quite well, and probably some high-level, also some high-level explanation that I can link after this lecture. Oh yeah, Michael is this deep learning day on Monday 14. So just after the finishing the Julia course, you can start this. You can go to this deep learning day. Okay, so let's suppose now that we want to actually compute the loss, so find if our define how good or bad is our model, and well, how can we define this function loss? Y hat The auto regularization layer, question, can you use the auto regularization layer? The part with probability 0.2, for example, and here we have a dropout layer. And yeah. So yes, you can do. I haven't. There are also a lot of tools for recurrent networks or kind of network that works on sequences and so on. I wanted here to illustrate only one simple example to introduce the package, the library. So let us define our loss function. For example, here we have we compute the output of our model on input x. We call it y hat. In case we have W, we have y hat. And we can simply use the cross entropy loss that is among all the predefined losses for in fluxes between y and y hat. So maybe define our loss function. We can also define what we're interested in is the accuracy of our prediction, which is different than the computing the cross entropy. So what we have is the opposite of one hot is the one cold, where it returns the index of the maximum value. And we want to compute the average we compute the average of the number of times we were correct in the prediction. This is our accuracy. We can decide, for example, which optimizer to use. There are a lot of defined optimizers. For example, the standard gradient descent is descent. We have, for example, we can use with nester of momentum, or maybe we can only want to use the Adam. Here is our optimizer. We use the full parameters for each optimizer, all its parameters. And we can also design some function that point out the loss every n seconds. This is easy because we have this turtle function from Flux that simply say, okay, call this function at most one time every n seconds. In this case, n equal 5. Now we can see, okay, we have an untrained network. We have our input, our output, what is the accuracy. And here we'll see a small warning. Don't worry about it. It's simply because I've converted everything to 64-bit floats, while Flux by default want to use 32-bit floats, which are more efficient, especially in when moving on GPUs, since Flux can make use of GPUs with CUDA. So we have actually that our accuracy is, well, 0.13, so a little bit more than 1 time in 10. So we are a random choice for now. So we can now train the network with the Flux train function, which takes the loss function to use which are the parameters that the optimizer is allowed to modify. And we have the Flux params of model. If we have a model obtained by chance and by combination of other predefined model, these params will contain all the parameters of the model. Using the batches that we have defined before, using this optimizer that we have just defined, Adam in this case, and uses the this callback function. And we perform 5 epochs. We actually have a macros that can simplify this code, but this is clearer for an introduction. We simply perform the training 5 times on the entire dataset, divided in mini batches of size, as defined before, 32 if I remember correctly. Now the training will take a little bit of time. That's why I use only 100 images, 1000 images, and only 5 epochs. And since I have converted everything in float 64 instead of float 32, we also using a little bit slower implementation. But just remember that if you want to use it for real data, Flux support GPUs, so you can move the training on GPUs. So the training has completed. Now the accuracy will have improved, but 67% of the time we are right is not the best by far, because the best is more than 99%. But for 1000 images and a few seconds of training, I think this shows that creating even not completely trivial models with Flux is quite easy. So is there any question about this part? How to include quadratic regularization? You can include it. I have to. Yes, you can include here in the loss function, and I would have to remember the regularization. I will have to check again what is the function to call for the adding the regularization, because now on at the moment I don't remember. I don't remember it immediately, but it is possible. Okay. Is there a way to save the model? Is there a way to save the model to a standalone file? Yes. You can save it with we're using the Bison.jl library, and you import the macro @save, and you can simply @save model and the file where you want to save it. And the same is @load, name of the file, and the model. And I see another question. I was wondering, because here loss appears to be a function of only of x and y, not of w. The thing is, you have the model inside the loss. So when you compute the loss, you can take for example here params of the model and do everything you want with the parameters of the model. So actually, yes, you have X and Y, but in some sense, the model, you can access the model inside the loss function and all the parameters. I hope this clarifies a little bit the, okay. Okay, so. Yeah. One thing we may want to do when working with Julia code is also to benchmark it. And, well, we have already saw in the previous lecture that we have at time and at time at markers to get the execution time of a certain function, certain piece of code. So let's try to, we want to benchmark the function mySum, which is simply a sum of all the elements inside the vector. Sum starts with 0. Actually, if we want to make it more generic, we may want to use 0 of L type of V, which means take the 0 of the type of the elements of V. So the function will be compiled differently with the correct 0 without type conversion if we use, for example, only integer, floats, or complex numbers, or anything that has a 0. But for now, let's simply use floating point numbers. And for each element of the array, sum it and return the sum. And let's use it with a random vector of 1 million elements, with a vector of 1 million random elements. If we time mySum, the first time we have 0.008 seconds, second time is faster. We have a lot less allocation, 220 kilobytes, 16 bytes. Why? Well, remember that Julian is compiled just in time, so the first execution will be slower than the second one. Because in the first execution, we have a compilation. In the second execution, we already have the compiled function. So if we only want to use time, remember to time not only the first execution, but also the second execution of the function. Obviously, the arguments can change. If they keep the same type, then the function is obviously not recompiled. But if you want to do everything automatically, the benchmarking automatically, we can use these packages, these library benchmark tools, which makes available the marker benchmark. We run the benchmark of mySum with a random vector. And it will take a little bit of time because it is executing multiple times, taking into account the variance of the execution time of each execution. So here we have a lot of statistics. So we usually allocate 16 bytes. We use between 1 and 2 milliseconds with the average that is a little bit more than 1 millisecond. And we have sampled this function 4,000 times. So let's compile it with the Python version of sum. And now, if we want to avoid also benchmarking the type conversion, we simply pre-convert the vector as a pi vector. So now is p and vec is a Python vector, which can be parsed without type conversion or copying. And we can benchmark by sum that, if you remember, we have imported at the beginning of the lecture from Python as the Python built-in sum. As you can see now, we have 5 milliseconds with up to 19 milliseconds. Obviously, there is a little bit of overhead in calling Python a different language from Julia, but even if you work entirely in Python, you will see that it is actually faster. Julia is actually faster. And let's actually benchmark the Julia built-in sum function. And we will obtain that Julia is actually quite fast in the benchmarking. We see 300 microseconds. So, well, 10 times, more than 10 times faster. And actually, if you want, we can modify this mySum function with a little bit of annotation. For example, we have bounds is a macro that actually say the next 4 cycles, don't bother with checking if everything is in bound. I assure you that everything is in bound. So disable and so on, so that actually, for example, for use seemed for use the accelerator, for example, vectorized instruction and so on, and actually have with only a few modifications our implementation of the sum that is as fast as the Julia native, the Julia built-in one. And is there any question about this part? And for all I want, because we are now at the end of the lecture, and well, we still have a few minutes, so if you have any question, please ask.
Excuse me, what was that other program you talked about when referring to neural networks?
Tensor Flow.
Yes.
The other framework is Tensor Flow, and Julia bindings are in TensorFlow .jl. I see also there is an observation on the chat. Here is another Julia-based framework for deep learning called KNet. Yes, there is also KNet. I haven't introduced it here because actually it is on my to-do list of things to learn because it seems interesting, but I haven't still had the time to learn and try it.